In this video, we're going to talk about quadratic functions. Sometimes we call them polynomials of degree 2, which differ greatly from linear functions, which we sometimes call polynomials of degree 1. And actually, chapter 3, we're going to be completely focused on polynomials of higher degree. We're going to be using a lot of the basic facts about linear and quadratic functions to sort of build up to more and more complex types of polynomials. Which we're going to spend a lot of time talking about and working on the general theorems of polynomials. Starting off with some reviewing some basic properties of quadratic functions. First of all quadratic graphs appear in the shape of a parabola, which looks a lot of times people would call it like the shape of an arc or an arch. And I wanted to actually mention before we get into that, parabolas are a very specific type of curve. There's actually a lot of different types of arches or arcs, whatever you want to call it, which are not to be confused with parabolas. There's actually a lot of different shapes. Like if you can imagine taking a necklace and hanging it on two nails hanging on the wall, that shape that it forms. Actually, early man thought that might perhaps be a parabola. But it's actually a different shape, which is called a catenary, which is modeled by a hyperbolic trigonometric function. And actually, we're not going to get into those functions in this class, but I was just trying to think of an example of a similar looking curve, which is not. So anyways, my point is parabolas have a very specific shape. They're very common in the real world because of the geometric properties they exhibit. Parabolas have what's called a focus, and one of the major benefits of parabolas is to reflect light into a singular point, or to reflect sound, or reflect other types of waves into a single position. So like a parabolic reflector, like a lens on a car light, could be shaped like a parabola to focus light in a particular direction. Or like a satellite dish is designed to collect waves into a singular point, the focus of the satellite dish. Parabolas are also quite important because they model the way gravity affects everything on Earth, and everything in the universe as far as we know. Like if you imagine shooting a basketball into a basketball hoop, that's another example of a parabolic arc, that shape. And technically, it's not a true parabola due to wind resistance and other factors in physics, but anyways, what I'm trying to summarize here is parabolas are very important shapes for a lot of reasons, and that's one of the main reasons we want to study them. But they're also very useful for algebra and calculus, as they have a lot of key principles. And parabolas or quadratic functions, either way you want to call it, have two major forms, kind of like with linear functions that we talked about in the last couple of videos from 2.3. And I like to sort of make connections to linear functions because we can remember a lot of the properties about quadratic forms based on those same comparisons. So and actually it depends on the textbook, but most people refer to the standard form, or some people call the quadratic form of a quadratic function to be ax squared plus bx plus c. Or basically, if you were to write a degree 2 polynomial just without any factoring, just using each coefficient in descending degree. And from algebra, you're probably used to polynomials like x squared plus 4x minus 5, or whatever, something like that. We would say it's in standard form, just written out in full. And so much like with linear functions, c is going to be the y-intercept. And again, that's pretty simple because if you plug in 0, both of these terms would turn into 0, and we'd just be left with c as the location of where it crosses the y-axis. And another useful reason to write it in standard form or quadratic form is because of the quadratic formula. And this is a formula I assume you guys remember. But I'm not assuming you have it all memorized. And we're going to review the quadratic form in great detail, so don't get worried. And actually, in our next live meeting, I wanted to actually talk about why is the quadratic formula true and how you actually can derive it. But in the quadratic formula, which we're going to review how to use and properties like that, which you probably recognize, there's it uses the letters A, B, and C, and so if we have it written in this form, it's useful for that reason. And recall that the quadratic formula solves the x-intercepts of the parabola, or we sometimes call them the zeros or the roots, or we just use it to solve a quadratic equation. And we're gonna review all that soon as well. But before we get into the quadratic formula and all that stuff, there's also a secondary form that we often may write a quadratic function in, which is called the vertex form. And basically, in this case, I kind of compare this to a linear function in slope-intercept form versus a linear function in point-slope form, where when it's in vertex form, we're listing it using a, which actually that's the only consistency between, obviously other than x and f of x, between a quadratic written in standard form and a quadratic written in vertex form. So that's just one thing that's always the same, is a, which we sometimes call the leading coefficient to the polynomial. But basically, notice that it's written in a different form. Instead of ax squared plus bx, it's a times x minus h squared plus k. And k and c are never going to be the same. They can be the same, but it's not very common. And h and b are not the same either, typically. And where h and k are reflective of the vertex. And the vertex is probably a term you remember, which is just a term for the penultimate point, or the tip point of the parabola. So like if it was a downward facing parabola or an upward facing parabola, the vertex is the point at the very bottom or top, which is a very important point on that curve. And the term vertex has other generic terms in math. Sometimes we refer to vertex in graph theory as just a point, but typically when you're talking about algebra, vertex is specifically referring to quadratic functions and not other similar curves. You wouldn't typically call it a vertex unless it's specifically quadratic. Anyways, it's not really worth splitting hairs about, though, to be honest. And anyways, one thing to be careful about is notice that it is f of x equal a times parenthesis x minus h squared plus k, which is a little bit weird, and sometimes I think students have found it hard to remember this. But I wanted to compare this. Actually, let me move back to the packet just for a second. So I'm going to switch from the slides into the written packet. And I wanted to kind of make a comparison back to, where is my stylus? Back to what we were talking about with linear functions. And the reason I'm going into this is because I think this will help you remember these formulas and a little bit easier. So I kind of made a comparison with the standard form of a quadratic function to the mx plus b form of the linear function. But so vertex form I like to think of as very similar to point slope form for a linear function, where we had a singular point and the slope of a line, and as long as we knew that, we could plug that in to find the equation. Similar to vertex form, a is sort of like the slope of a parabola. It's not exactly the same, but it determines the steepness and the direction of the parabola. A, kind of like m does with a line. And h and k are sort of like point slope form, where you can plug in x1, y1 to get a specific point on the line. But with a parabola, h and k is specific point, the vertex. So you can't plug in any point into the formula, but it's very similar. So let me actually move over to the side because I wanted to just sketch something out. And I found this helpful for remembering it. But if we remember the formula y minus y1 equal m times x minus x1. If you, but basically, if you were to just square this term, what this would leave us with is the vertex form for a quadratic. But instead of using m and x1, y1, we would use a, h, and k for that of a vertex. And my point is, this is not a perfect comparison, but this is a way that you can remember the vertex form. And notice the only difference between it written as a function is, well, we could add k to the other side to solve for y. And if we solve for y, then we have it in function form. And all parabolas, well, not all parabolas, all vertical parabolas are functions. If you change the location of the square to the y, it would actually change the orientation of the parabola to be horizontal, which would not be a function. And that's why we don't typically look at equations like this when we're talking about functions, because those are never functions due to the orientation being sideways. But anyways, that was kind of my point. I don't know if that was helpful. Let's move on from that because it's not super important, but that's how I see it. I see it as very similar to the point slope form. And that being said, you can use either one of these formulas to craft the equation or the formula for a quadratic. Now finding a, there's not a simple formula like we have for slope where you could just find the rise of a run, but you can use the information at hand to go ahead and find that. So in the next video, I'll go ahead and wrap this one up. And I apologize that it says linear functions. I just noticed that it should say quadratic functions, and I'll fix that in the next video in the bottom. But next up, I want to talk about how do we switch from form to form? Because back with linear functions, when we were in y equal mx plus b, or y minus y1 equal m times x minus x1, it was very easy to switch between the forms just by using multiplication. With quadratics, it's a little bit more annoying, and I wanted to review the process of changing from standard form to vertex form. And it's useful because in standard form, one of the weaknesses is we can't tell what the vertex is without doing any work. Actually, there's a formula for it called the vertex formula, which is in the packet, but there's an algebraic procedure which can convert a quadratic like this into a completed square. And this is something that is of an important skill to have in math because it appears later in calculus and various places, and it's just something you should be aware of. So this is something I would definitely put on a test, and in the next video we'll focus on how we do that.